In the ocean, there are organisms that were never crabs and are not even closely related to them. Yet, over millions of years, they gradually take on a crab-like form with measurable precision. Some species develop a carapace up to about 28 centimeters wide, roughly the size of a standard dinner plate, and a leg span that can reach nearly 1.8 meters. Their bodies flatten, their tails shrink and fold underneath, and their movement shifts to sideways locomotion. This transformation has occurred at least 5 separate times across different evolutionary lineages. This is not an isolated case. It is a recurring pattern. And the question is no longer whether this resemblance is real, but why evolution keeps returning to the same structure, as if solving the same biological problem again and again. Carcinization is the term used in evolutionary biology to describe a process in which multiple crustacean lineages independently evolve a crab-like body plan. This includes a broad, flattened carapace, a reduced and tucked abdomen, and a shift towards sideways locomotion. Importantly, many of these organisms are not true crabs in a taxonomic sense. They belong to different branches of the crustacean family tree, yet converge on a remarkably similar morphology. This is not a random coincidence. It is a documented pattern observed across fossil records and modern species, indicating that under certain environmental and structural conditions, evolution repeatedly favours this specific anatomical configuration. If carcinization is real and repeatedly observed, then the central question is not whether these organisms resemble crabs, but why this specific body plan emerges so often. What underlying pressures drive unrelated species toward the same structural solution? Is it purely a response to environmental constraints, or does it reflect deeper limitations in how biological systems can adapt? More importantly, why does this pattern appear predominantly in crustaceans and not across all forms of life? These questions define the boundary between simple description and true scientific explanation. Convergent evolution provides the fundamental mechanism behind carcinization. It describes a process in which unrelated organisms independently develop similar traits because they are exposed to comparable environmental pressures and functional constraints. These similarities do not arise from shared ancestry, but from shared problems that require efficient solutions. In aquatic environments, factors such as stability, protection, and mobility create a limited set of viable structural designs. As a result, different crustacean lineages, despite diverging millions of years ago, can evolve toward the same crab-like morphology. This pattern is not unique to crabs. It appears in multiple systems across biology, where form repeatedly aligns with function under consistent physical and ecological demands. What is firmly established is that carcinization has occurred multiple times across distinct crustacean lineages, supported by both fossil evidence and genetic analysis. It is also clear that the crab-like body plan offers functional advantages in certain environments. However, what remains uncertain is the full extent of how many times this transition has happened, especially in lineages that left incomplete fossil records. It is also incorrect to assume that all evolution trends toward this form, as its occurrence is constrained by anatomical starting points. A defining feature of crab-like morphology is the development of a wide flattened body, which directly influences stability. By lowering the center of mass, this structure allows the organism to maintain balance in dynamic environments such as shallow coastal zones, rocky seabeds, and areas with strong wave action. A compact, flattened form also reduces the likelihood of being overturned, a critical vulnerability for many marine invertebrates. In addition, this body plan enables access to narrow crevices and spaces beneath rocks, providing both shelter and protection from predators. From a mechanical perspective, this is not an arbitrary shape, but a highly efficient solution to environmental constraints imposed by life near the seafloor. Another critical component of the crab-like form is the development of a rigid exoskeleton that functions as an integrated protective system. Unlike elongated crustaceans, where segments remain more exposed, the crab's body is consolidated into a compact, shielded structure. This reduces vulnerable surface area and distributes external forces more evenly across the carapace. The result is a form that can withstand predation attempts, physical impacts, and environmental stress with higher efficiency. Rather than serving as passive armor, the exoskeleton operates as a structural reinforcement, turning the organism into a mobile, self-contained unit, optimized for defense and durability in complex marine habitats. Crab-like organisms also exhibit a distinct modification in limb structure, characterized by shorter, more robust legs that enhance control and stability. This configuration allows for precise movement across uneven substrates such as rocks, sand, and coral surfaces. One of the most notable adaptations is lateral or sideways locomotion. Unlike forward dominant movement in many other animals, sideways motion enables rapid directional changes without reorienting the entire body. This provides a tactical advantage when evading predators while maintaining visual and defensive alignment. From a biomechanical perspective, this form of locomotion is highly efficient in confined or irregular environments where flexibility and responsiveness are critical for survival. Taken together, these traits form a coherent structural system rather than isolated adaptations. A flattened body improves stability, a rigid exoskeleton enhances protection, and specialized limbs enable controlled, responsive movement. Each component reinforces the others, producing a compact and resilient design suited for complex marine environments. This is why the crab-like form is not an accidental resemblance, but a repeatable outcome. Under similar physical constraints, evolution does not generate unlimited solutions. It tends to converge on a limited set of configurations that consistently perform well under pressure. Lobsters represent a highly successful crustacean lineage, surviving for hundreds of millions of years with relatively stable morphology. They possess strong exoskeletons, powerful claws, and effective locomotion, indicating that their body plan is functionally viable. However, despite these advantages, lobsters have not repeatedly evolved into crab-like forms. This suggests that evolutionary success alone does not determine morphological direction. Instead, it highlights that different structural starting points impose different constraints. While both crabs and lobsters are well adapted to their environments, only certain anatomical frameworks allow for the specific transformation associated with carcinization. The elongated, segmented body of lobsters introduces significant mechanical constraints that limit how their morphology can be altered. Their abdomen is large, muscular, and essential for propulsion, particularly in rapid escape responses. Compressing or reducing this structure, as seen in crab-like forms, would require extensive reorganization of musculature, joint articulation, and neural control. Each segment is functionally integrated, meaning that modifying one part affects the entire system. Evolution does not easily permit such large-scale restructuring without compromising survival. As a result, the lobster body plan remains relatively stable, not because it is inferior, but because it is structurally less flexible for this specific evolutionary pathway. In contrast, the crab-like body plan emerges from a structural framework that is inherently more adaptable. The reduction and folding of the abdomen beneath the body allow for a more compact form without disrupting core physiological functions. This compactness enables incremental modifications, such as widening the carapace or reinforcing the exoskeleton, without requiring a complete redesign of the organism's internal systems. Limbs can shift in orientation and function with relatively lower structural cost. In evolutionary terms, this represents a pathway with fewer constraints. Rather than demanding radical transformation, it allows gradual adjustments that maintain functionality at each stage, making the transition toward a crab-like morphology more attainable. Current evidence strongly supports the idea that carcinization occurs more readily in certain crustacean lineages due to structural flexibility and functional advantages. However, this does not represent a universal rule of evolution. There is no deterministic pathway forcing all organisms toward a crab-like form. Instead, this pattern reflects a constrained set of viable solutions under specific biological and environmental conditions, rather than a fixed evolutionary endpoint. In biological classification, true crabs refer to members of the infraorder Brachyura, a group defined by specific anatomical features rather than superficial appearance. These include a broad, flattened carapace, a significantly reduced abdomen folded beneath the body, and a distinct arrangement of limbs adapted for lateral movement. This classification emerged historically from morphological observation, long before genetic analysis was available. As a result, organisms that resemble crabs are not always closely related to them. The term true crab therefore reflects both evolutionary lineage and the limitations of early taxonomic methods. Despite their appearance, not all crab-like organisms belong to the true crab lineage. King crabs, for example, are genetically closer to hermit crabs than to Brachyura. Over evolutionary time, their ancestors abandoned the use of external shells, developed a hardened body, and gradually adopted a crab-like form. Similarly, porcelain crabs belong to a separate group known as Anomura, yet display a strikingly similar body structure. These cases illustrate how distinct evolutionary paths can converge on nearly identical external designs. The resemblance is often so strong that it obscures their true relationships, creating the impression that nature is repeating the same blueprint across unrelated lineages. Fossil records reveal that crab-like forms appeared even before the emergence of modern true crabs. Early organisms such as Eocarcinus display partial characteristics of the crab body plan, including a broadened carapace and a more compact structure. However, these early forms did not fully achieve the stability and efficiency seen in later lineages. Many lacked reinforced exoskeletons or the limb configuration necessary for controlled lateral movement. As a result, numerous early attempts at this morphology did not persist. These extinct forms suggest that carcinization was not a single event, but a repeated process of evolutionary trial, where only the most functionally optimized designs endured over time. At this point, the pattern becomes difficult to ignore. Multiple lineages, separated by millions of years and different evolutionary paths, arrive at nearly the same structural outcome. This raises a deeper question. Is this simply a consequence of functional optimization? Or does the repetition itself reveal something more fundamental about the limits of biological design? When the same form emerges again and again, the explanation may be scientific, but the impression it leaves is something else entirely. Humans are highly sensitive to patterns, especially when those patterns appear repeatedly across unrelated contexts. When similar forms emerge independently, the brain tends to interpret this as intentional or meaningful rather than coincidental. This response is rooted in cognitive bias, where pattern recognition evolved as a survival mechanism. Detecting regularity could signal danger, opportunity, or hidden structure. However, this same mechanism can lead to overinterpretation. In the case of carcinization, the repeated emergence of a crab-like form may feel purposeful, even directed. In reality, it reflects constrained biological possibilities, but the human mind is predisposed to perceive it as something deeper or unexplained. In many coastal cultures, hard-shelled marine organisms were often interpreted through a lens of uncertainty and symbolism rather than biological understanding. Creatures with rigid exteriors, sideways movement, and exposed eye structures appeared unfamiliar compared to terrestrial animals. When such organisms appeared in large numbers after storms or washed ashore unexpectedly, they were sometimes associated with omens, imbalance, or environmental disruption. Without knowledge of molting cycles, reproductive patterns, or tidal behavior, these events could be perceived as irregular or even unnatural. These interpretations were not irrational, but responses shaped by limited information and the human tendency to assign meaning to unfamiliar biological phenomena. Molting in crustaceans involves the periodic shedding of the exoskeleton to allow for growth. During this process, the organism exits its old shell, leaving behind a nearly complete external replica of its body, including limbs, eye structures, and surface details. To an untrained observer, this discarded shell can resemble a lifeless but intact organism. In certain conditions, especially when multiple molts accumulate in one location, the scene can appear as if numerous identical bodies have been abandoned simultaneously. This visual effect can be unsettling, as it suggests a form of transformation where the original organism has seemingly disappeared, leaving behind only a hollow structure that mirrors its previous form. The sense of mystery arises not from the phenomenon itself, but from how it is interpreted. Carcinization, molting, and mass appearances of crustaceans all have well-established biological explanations. However, when these processes are observed without context, they can appear irregular or even unnatural. The boundary between scientific reality and perceived anomaly is often defined by the availability of information. What seems inexplicable is frequently a reflection of incomplete understanding rather than evidence of anything beyond natural processes. What is most strongly supported by current evidence is that carcinization is a repeatable evolutionary outcome within certain crustacean groups. Given the right structural starting point and environmental pressures, the transition toward a crab-like form becomes a viable and efficient pathway. This does not occur randomly nor universally, but within a constrained biological framework where certain designs consistently offer functional advantages under similar conditions. The unease does not come from something supernatural. It comes from recognizing that nature repeats itself, not endlessly, but within boundaries we are only beginning to understand.